He comes from the gates of Zion. He comes from the gates of Zion. He comes from the gates of Zion. He comes from the gates of Zion.
Alright, my name's Herschel B. Weather. I'm a professional cowboy as well as a professional mathematician.
And I'm Robert Franco. I'm a pipe engineer. We're gonna be fixing the old drain today. City Council told us so.
I'm really interested in related rates. I hear that there is a pipe leak in that pipe down there. So we're going to try and calculate the rate at which the height is changing so that we can find the rate at which the volume of the water in the pipe is changing when it is at 1 meter high.
Let's get started. You know, they say there's a giant rat of some sort down in these here pipes. I don't care about rats, all I care about is finding
The change in volume over time.
well,
Specifically, at when the height is 1 meter.
I see.
It's my special.
The water level is rising pretty steadily now.
Yeah, it looks like it. Seems to be at a constant rate.
Oh, jeez.
Alright, well, this looks like a good enough place as any to set up shop.
You get to calculating, I'll take a look deeper down and see what we're dealing with here.
Alright.
The damage doesn't seem natural.
Alright, let's do this. Alright, so according to my calculations, the volume of a horizontal cylinder, such as this, is equal to...
Holy shit.
Alright, so we're just... Herschel! What is it, Robert?
There's something out there, something rather large.
I think we should get out of here.
He comes from
No,
the gates of Zion. He comes from the gates of Zion. He comes from the gates of
Oh my god! We're gonna have to figure this calculus back at home. Luckily, I got all of the measurements I'm gonna need, so that's good. Alright. Okay, well, we managed to survive the Ratman attack, and luckily, I got all of the values that we needed, so we're gonna go ahead and do the problem. Okay, so with the related rates problem, first you need to start out by making a sketch of what you're finding the related rates of. So, we're finding the related rates of a horizontal cylinder where water is filling up the bottom. Next, we need to establish all of the measurements that we took. So first we have the length of the pipe, L, then we have the radius, and then we have the height of the water. So, the pipe that we were exploring, the length was 20 meters. The radius was 1.5 meters. So these are constants. They didn't change because this was just the shape of the cylinder. However, the height of the water was changing. So, instead, we need the change in the height of water over time. So, I measured the change in the height of the water over time and found that it was a constant equal to 0.1 meters per minute. So now that we have all of our values, we can set up the volume problem. So the volume is equal to L times R squared times the inverse cosine of R minus H over R minus r minus h times the square root of 2rh minus h squared. Remember that all of this is being multiplied by L. Now, we're going to take the derivative of this so that we can find the change in volume over time using these measurements as well as the measurement h equals 1 meter. So this will find us the change in volume over time when h equals 1 meter. So, now we're going to take the derivative of this. So, we get dv over dt is equal to, we're going to start with power rule. So remember, L and R are constants. So whenever you take the derivative of either L or R, it's going to be equal to 0. So, starting with power rule, we would have the derivative of L times this. Since the derivative of L is 0, that cancels out. So we get L times the derivative of this. So we're going to start out with this. This will be the derivative of r squared times the inverse cosine of r minus h over r. This is a constant, so that cancels out. So we just get r squared times the derivative of the inverse cosine of r minus h over r. The derivative of an inverse cosine is equal to the negative derivative of whatever is inside of it divided by the square root of 1 minus whatever's inside squared. So that means that this is going to be r squared times negative the derivative of r minus h over r. This is the same as r over r minus h over r, which would be 1 minus h over r. The 1 will cancel out, so then we would get 1 over r times dh dt divided by the square root of 1 minus r minus h over r squared. And then we're going to subtract the product rule of this. So we're going to get the derivative of r minus h, r cancels out, so we get negative dh dt times the square root of 2r minus h squared. So then we're going to add r minus h times the derivative of this. So we will get r minus h times, so then it's going to be 1/2 times what's inside there, so 2rh minus h squared to the negative 1/2 power times the derivative of what's inside there. So the derivative of 2r times h is going to be 2r h dh dt minus 2h dh dt. And that is our derivative. So I've condensed all of this. Our dv dt is equal to all of this, and then this times that. So now we just plug everything in and solve for dv dt. Right? So we get dv dt equals 20 times 1.5 squared times 1 over 1.5 times 0.1 divided by the square root of 1 minus 1.5 minus 1 over 1.5 squared minus negative 0.1 times the square root of 2 times 1.5 times 1 minus 1 squared. And then this is going to be plus 1.5 minus 1 times 1/2 times 2, 1.5 times 1 minus 1 squared to the negative 1/2 power times 2 times 1.5 times 0.1 minus 2 times 1 times 0.1. And then we're just going to plug everything into our calculator and solve for dv dt.
So it should look something like this.
Alright, so I've done all the math and I found that if you have 20 times 20.159099, then it's going to be minus the product rule. This was a negative, so it's plus 0.14142, and then minus 0.017677. So, it's taking a long time, as you can tell by my alpha change, but I got the answer. So dVdt should equal 5.657 meters cubed per minute.